engineering dynamics, kinetics of a particle, curvilinear motion, this time in r and theta coordinates or polar coordinates. So if this time we have a particle like a ball moving through a curved line, and we want to see the components of velocity and acceleration in a direction of motion like radius, and also the angle of rotation like u theta. Last time we reviewed the motion in terms of velocity and acceleration in normal and tangential motion, but this time we want to see the same effect like a u, r, and u. If we want to say it in a language of mass, it's like the previous time was like a Cartesian coordinates, and for example this time it's a polar coordinates. In curvilinear motion like r theta, we have a radius and a theta. So r displacement is the numeric value, vector of displacement is the numeric value of displacement times the unit vector of displacement like u sub r. Likewise, if you make a derivation of that, it just gives you from displacement you can derive velocity, and that's r dot, and that means the derivation of the first part r dot times u r plus r times derivation of the second part, that's u dot r. Let's see what u dot r is. So if you take a closer look on what happened in u dot of r, that's the limitation of delta u r when you from a u r to prime r in a very small time frame, like delta t goes to 0. That you can call it like the limit of delta u r over delta t in a very short matter of time. And that's exactly like you can write it like it's a limitation of delta theta over delta t times ut. So you can easily see we can call this angle like a delta theta. A small variation in the angular change, and if you get to the direction of normal vector for that one, that's definitely ut theta. That's in y direction, and our y direction is theta. So u dot r can be replaced by a theta dot. You can replace delta theta over delta t by theta dot times u theta. And then you can replace it in the formula of velocity, which is r dot, that's r dot u r plus r dot u dot r. So one can say the velocity is vr times the r and v theta, radius component of velocity, angular component of velocity, times their own unit vector of r u sub theta. And again, one can easily say you can cancel out ur with ur, and vr is identical to r dot. And for the second part, if you call this equation 1 and a, and this one like b, equation a and b says that v theta, if you can cancel out this one with this one, v theta is equal to r times theta dot, r times theta dot. So one can say the magnitude of the velocity r and theta component coordinates is a square root of r dot square plus r times theta dot in parentheses a square. That's the magnitude of velocity r and theta coordinates. Why we are interested in r and theta? It's like polar coordinates make a lot of dynamics a problem far simpler in comparison to the other coordinates. But again, I'm insisting that all the problem you can solve them from a different method which you prefer. So again, if v is r dot and r, that's r dot times u r plus r times u dot r, which u dot r, we just see that that's equal to theta dot times u theta. And if we want to derive the acceleration field from the velocity, that's a derivation of first component plus derivation of the second component, which is r times theta dot times u theta. Let's see how we can create them. So the first part, the first derivation, it just says that's a derivation of first component times the other one. So that's the original one was r dot, so that's r double dot times u r plus u dot r times r dot. Derivation of the second part times the original part, the first part. And for this part, we do have a three components. So let's say for the first part, we just derivate r, and let's do not touch the rest. So that's r dot plot times theta dot plot times u theta. So we didn't touch these two. We just derivate the first one. Last next time we just derivate the second part. So that's a theta double dot and remains r and theta intact. And for the last part, we just derivate the last part, and that's derivation of u theta. That's u dot theta times r times theta that we touch the two others. So for each part, we just derivate that component and remains the rest like intact. So it just says if this is the equation 2, derivation 2, let's make it a bit cleaner. So let's see what is u dot theta. So if this is a radius direction, u unit vector in radius direction, and that's our the y-axis is radius vector in theta direction. If we just move from u theta to u theta to dot theta, and this is a change of that. From here, we just move to dot theta. And can easily see u dot theta is a limitation of delta u t over delta t. And that's a negative times a of delta theta over delta t. That's our delta theta over time span. This is our delta theta over delta t times u r. How is that? You can easily see the direction of this vector. That's in negative u r. So that's how this negative, and let's make it a bit clean, might see it better. That's how this negative and u r makes sense. This is negative because we are in a negative of delta u. T is in a negative direction of u. So that's a negative r in terms of the direction for that. So if we just create a u dot theta. So one can say u dot theta is a negative, and replace that by theta dot. A negative theta dot times u r is a negative theta dot times u sub r is theta dot u dot theta. So place it in the main equation. So u theta dot is equal to negative u theta dot is equal to negative theta dot times u r And if you just multiply it by r times theta dot, it just gives you a negative r times theta dot square times ur, the overall what we have there. So a is like ar, radius component of acceleration, times the unit vector of radius, which you can see here, and the theta rotational component of the acceleration times u theta. And if you add the identical term with each other, it just gives you a is equal to ar is r double dot minus r times theta dot square times ur plus in parentheses r times theta double dot plus 2 times r dot times theta dot. And how is that? One of them is just coming from here, and that's r times u dot, that's r times theta dot ut, and the other part comes from here. So if you add both terms, it just gives you 2 times r dot theta times ut. So it just says our acceleration in r and theta component is just r double dot minus r theta squared r, and this is ar, and this component is a theta. Hmm? And it just says in r and theta we have two components for acceleration, which is ar is r double dot minus r times theta dot square, and a theta is r times theta double dot plus 2 times r dot times theta dot. And if you just use these two equations, it just makes a lot of problem far simpler. We just put it into example in next video. Thank you.